Hello and welcome to my tutorial on some advanced integral calculus. This is my first tutorial video on calculus. It's also my first time kind of like really using this Wacom tablet, so forgive my bad handwriting on screen. But I thought I'd make this tutorial series because one of the things I do when I'm trying to learn something is to teach it to an imaginary person. And I thought, if that's helping me learn, why not take what I'm teaching to another person and just put it together in a tutorial in this particular playlist. I'm going to be focusing on advanced integration techniques. So watching this video, you should already understand what an integral is, how to take an integral, use substitution, and then the applications of integrals such as surface area or volume. And in this video, we're going to be discussing 5 methods that you can use to take more advanced integrals. The first one is substitution, and not just basic substitution, but a little bit more advanced substitution. Splitting, division with rational fractions. It is completing the square, and it is multiplying by 1. So these are the 5 techniques that we're going to discuss in this video alone, and this video is going to be more of an intuition or kind of like an explanation of what these techniques are without going into problem solving. In future videos I may just solve some example problems to help walk people through it and just discuss kind of my thought process. So let's start with substitution. Substitution you should have already done by now. Let's use an example that's a little bit more complex. We have 1 over e to the x plus e to the negative x. We can't exactly pinpoint what we need to find for our u substitution, right? If we use e to the x for u, right? So our derivative is e to the x dx. And once we've plugged in our e to the x down here, we don't have an e to the x by which we can multiply our dx, right? And so this is kind of where integrals separate themselves from derivatives. It's no longer a process. You have to be kind of inventive, intuitive here if you're going to want to solve this problem. One thing you might say is, okay, this is negative x in the bottom. It looks a little bit fishy. It doesn't look right. Maybe we can multiply on the top and the bottom by e to the x. And remember, this is a perfectly fine operation because e to the x divided by e to the x is just 1, and 1 times an integral is still that integral, right? And so we'll have e to the x over e to the 2x plus 1, right? E to the x times e to the x is just e to the 2x, and then e to the x times e to the negative x is just 1, right? And now if we subbed in our e to the x, now we can plop a du in here because du is equal to e to the x times dx, and we have that e to the x times dx, right? So first of all, we can get our du in here because du is just e to the x times dx. And then we have our u squared down here because this e squared x, right, can be rewritten as e to the x squared, right? And we know that e to the x is just u, so we get u squared here. So that's why we got that u squared down here. And then we add to that 1, right? Now this is a significantly easier substitution problem to deal with than what we had before. What we can see here is that it looks kind of like, it looks like one of our trigonometric identities, right? And these you have to have memorized. You have to have these on your belt. You have to understand that 1 over our value squared plus 1 is just equal to the arctangent, right, of our value, okay? And these can get a little bit more complex. If you have like a 4 here, then it would be over 2 because 4 is 2 squared, but that's will be discussed later. But just remember that this form, 1 over x squared plus 1, right, is equal to the inverse tan or arctan of x, right? That's just one thing that you have to memorize. So by the time we've reached this integral, right, we can just write this as arctan of u. And if we sub our u back in, we get arctan of e to the x. I cannot explain to you any method that will allow you to solve these problems easier. You just have to understand these kind of subtle substitutions and take advantage of your own problem-solving skills. And you'll understand this, with enough experience and with enough time. And I'm going to do one more example here, just so you know how to do one of these. So let's take another one that's looks more like this. Let's go sine cubed x over cosine 5x. And again, this is all problem-solving skills, right? If I were to look at this by myself, I have enough experience doing integrals that I can say I see a tangent and a secant thing going on here, right? I can rewrite this as the tangent cubed x times 1 over cosine squared x, right? And we know that this 1 over cosine squared x can just be rewritten as secant squared x, right? So we're going to use our u to be tangent x. The derivative of tangent is secant squared x dx. There we go. And so we got a perfect substitution problem right here, right? This secant squared x dx is just du. And our tangent is just u. And if we find the integral of that, right, it's u to the 4th over 4, which we can sub back in our tangent, and we get tangent 4x over 4. So the next technique we're going to talk about is splitting fractions. Splitting fractions is, for some of you, this might be a relief, but it's significantly more plug and chug than problem solve, right? You don't need to have a big brain to be able to solve splitting fractions or to operate on integrals by splitting their fractions, right? And without even introducing an integral sign, we're just going to talk about, splitting fractions. So the general gist is that a plus b over c can be split into a over c plus b over c. And for a practical example to understand, what this means, why this is important, or if this actually works, let's go 1 plus 1 over 3. Very simple, right? We got our a is 1, b is 1, c is 3. This can be rewritten as 1 over 3 plus 1 over 3, right? 1 over 3 is 0.3, 1 over 3 is 0.3, so we basically get 2 over 3, or 0.6, right? This is a perfectly valid way to split a fraction. If I had 2 over 3, I could rewrite that as 1 plus 1 over 3 is equal to that, right? I apologize for the heater in the background turning on. Splitting fractions is not just limited to, two numbers, right? We can have a very complex expression over here, right? Let's just say it's over 3 or something like that. We can split this up as x squared over 3 plus 3x over 3 plus 4 over 3, right? Or, we can kind of segregate that one part, and we can rewrite this as who knows, x squared plus 3x over 3 plus 4 over 3. It all comes down to our preference, whatever we think is the most convenient, however works to our advantage for solving a problem. Splitting fractions is not just limited to, basic algebraic or numeric, functions. We can use something that's more trigonometric, like let's do plus sine cubed x. I'm just giving an arbitrary example to show you the power of splitting functions. Let's say over secant x, right? We can rewrite this as cosine x over secant x plus sine cubed x over secant x. And that can even be rewritten further as cosine squared x plus sine cubed x cosine x. Because remember, cosine x is just equal to 1 over secant x. So 1 over secant x is equal to cosine x, right? We can just move it back to the top. Now, if this was an integral, right? If we had an integral right here that we were taking of, this would make it significantly easier, because right over here we can do u substitution with u being sine of x and our du being cosine of x, and then we can find the integral very easily there, and we can use a half-angle identity, which we'll talk about in a later video there. But it just goes to show that splitting fractions kind of makes these integral problems significantly easier. It simplifies them so that it's a lot easier to operate on them. And when you're on a test, this can come to your advantage, especially if the professor gives partial points. So let's go x plus 2 over x squared plus 4. And we're going to do an integral here. Now, if you were just to look at this integral for the first time, this plus up here should set off, red alarms or red flags in your head telling you that you can split this fraction and make the integral significantly easier to solve, right? We could do the integral of x over x squared plus 4 plus the integral of 2 over x squared plus 4. And see, all I did was I just split it up right at this point, and I made it into two separate integrals. And then we can solve each one independently. If we wanted to solve this first one, right, which we'll do down here, we might do u substitution. This looks like a good place for u substitution. We can go x squared plus 4, and then our du would be equal to 2x dx, right? Very simple. And in our problem right here, we'll toss in those dx's. I'm pretty lazy. I don't like to write the dx's. And then we can rewrite this expression, right, this integral, as 2 over 2, right? Multiplying by 1 does not do anything to change the value of the integral at all whatsoever. Stays the same. We write 2 over 2 x dx over x squared plus 4, right? So we have the same integral right here, down here, and now we can apply our u substitution. Our du is just going to be this 2, this x, and this dx, and this x squared plus 4 is going to be our u, and then we're left over with a 1/2, right? And if we took the integral of this, right, the integral of 1 over u, because this du over u is the same thing as 1 over u times du, but the integral of 1 over u is just going to be the ln absolute value of u, and then we multiply by our 1/2 by the constant multiplier integral rule, right? And then we reintroduce our u, which is x squared plus 4, to get 1/2 ln x squared plus 4. And that's our final integral just for this first integral up here. So I'm going to clean this up to make it look a little bit nicer. Now we move on to our second integral. And if you have spent enough time finding integrals and finding derivatives, you'll be able to tell that, with our constant multiplier rule, we can drag this 2 outside, and we can rewrite this as just 2 times 1 over x squared plus 4. And by this point, you should be able to tell that this 1 over x squared plus 4 is the form of arctangent. And so all that this integral is equal to is 2 times the arctangent, right, of x over, and this is our a right here. The general form of arctangent, which you should definitely memorize when working with these, is 1 over x squared plus a squared, right? And the integral of this is equivalent to arctan of x divided by a all over a, right? That is just a rule that you have to memorize on your own. So we do x divided by a. Our a, right, this 4 can be rewritten as 2 squared. We got our a right there. We divide that by, what is it, a again, 2. And so those 2's cancel out, and you're just left with your final integral of x plus 2 over x squared plus 4 is ln x squared plus 4 over 2 plus arctan x half, right? And it looks complex, but with enough time, you'll be able to figure this out. And if you were to try and solve this problem without using splitting fractions or without using another type of technique, it would be significantly harder, right? So let's move on to the next technique. We'll focus on the next technique, which is division with rational functions, right? And division with rational functions is quite simple. And let's start with algebra. Let's start with the more basic example, the rule that this comes from. Let's say you have a function that looks like this. We're not taking an integral right now, we're just focusing on the algebra. Let's say you have a rule, or a function that looks like this. If I wanted to simplify this function any further, for whatever reason, I could do division of rational functions, right? So I could say x squared plus 2 divided by x minus 1, right? Now x, what do I have to multiply this x by to get x squared? Well, it's x, so we go x squared, and then minus x, and then we subtract that, right? This is just basic long division, but with functions. If you haven't learned this yet, I advise you to go learn it. You can watch it on Khan, very simple. So we get 0 plus x, because those two minuses give you a plus x. And then what do I have to multiply? And then we bring down our 2 over here. What do I have to multiply this x by to get x, right? You just multiply it by 1. We subtract 1 times x minus 1, right? Because 1 times -1 is -1. And then this becomes 0, and then a negative times a negative is a positive, plus 3, right? So this whole expression can be rewritten as x plus 1 plus 3 over x minus 1. And this may not look, entirely useful, but in the context of integrals, if you're trying to take an integral of this, you're going to have a bad time, right? But if you're taking the integral of this, you can take the integral of x, which is just x squared over 2, plus the integral of 1, which is just x, plus the integral of 3 over x minus 1. And we can use a fancy u substitution to determine that this is just I think it's something like 3 ln x minus 1, right? And can go through those steps to figure out the integral just by dividing, and you can simplify your integral significantly more than if you had left it alone in this form. And that's the power of divisions with rational functions. So I'm just going to do one more example to kind of lead you through, how I would think about this. Let's start with, let's do one that's like x cubed minus 2 over x plus 1, right? We can rewrite this as, right, we're going to find the division here. And I'm going to just skip this part, but you should be able to probably do it yourself. So this can be rewritten as, So this can be rewritten as the integral of x squared minus x plus 1 minus 1 over x plus 1, right? We can rewrite it that way, and then we can find the integral of this, which would be very simple: x cubed over 3 minus x squared over 2, and so on and so on. We use u substitution for this one right here, and we'll probably end up with minus ln absolute value of x plus 1, right? So that's the general gist of division with rational functions, allowing you to kind of simplify your expressions, make them a lot easier. Now we'll move on to the next one, which is completing the square. And this one, again, just basic algebra. So if you don't entirely remember how to complete the square, I'll just do a very quick example to kind of refresh your memory. Let's say you have some function like this, right? X squared plus 6x plus 13. Okay, how would you be able to simplify this expression, right? Well, this doesn't simplify down into anything. There's nothing that, when added together and then multiplied, gets 13, obviously, because 13 is a prime number. So we have to try and figure out a way to more effectively, right? And one thing that we can do is what's called completing the square. We just take this part right here, right? And we operate on this entire expression to drag out a square. And what do I mean by that? Well, x plus n, right, plus 13. If I am able to figure out some n, right, where I will get a rational expression plus, we're going to take a new variable y, squared, right? There has to be some value n that I can add here to turn a function here, right, into a square, and then add 13 on the end, if that makes sense, right? And the general method by which you can do this, it's very simple. To complete a square, to find that expression, which is a rational function that kind of turns it, that squared to get the same exact expression, is to kind of isolate the terms that you want to complete the square of, which we'll say is x squared plus 6, right? And then if we want to complete this square, we take the second term, the b term, right? This is a, this is b, and then our c would go right here. This is our c. We take the b term, divide it by 2, right? This is a 6 and a b at the same time. we take the second term, we divide it by 2, right? And then we square it, which in this case will be 9, because 6 divided by 2 is 3, and that squared is 9. And this will allow us to complete the square here, right? So we can rewrite this as x squared plus 6x plus 9, right? But in order to complete the square, we have to make sure that the value of the expression stays the exact same, right? And we can't just add on a 9 out of nowhere without compensating for it, right? This is a perfectly valid expression. It does not change the value of the expression. This is also a perfectly valid expression. It does not change the value of the expression at all, because 9 minus 9 is still equal to 0, right? This is similar to when we're using division, when we multiply by 1 on the top and the bottom, right? It doesn't change the value of the expression. And so we can rewrite this as x plus 3 squared, right? Because this function right here, this x squared plus 6x plus 9, that's just x plus 3 squared minus 9, right? That's all we did, is we turned it into a square. And this is called completing the square. We get some rational expression squared, right? And that makes everything significantly easier for reasons I will show right now. Let's say you have some integral, right? And we're just going to use the exact same example here. And that integral is 1 over x squared plus 6x plus 13. This is an extremely complicated integral to try and solve on the fly. But we can simplify this by completing the square. And the way you should know to complete the square sometimes, right, the red flags that should go off when you're trying to complete the square, is if you kind of see this general form of x squared plus 6x in either the numerator or the denominator, right? And we can rewrite this as 1 over x plus 3 plus 4. Why plus 4? Because if we go x squared plus 6x plus 9 minus 9, and then we complete the square, we get x squared, or x plus 3 squared, right, minus 9 plus 13. And 13 minus 9 is just 4, right? So we have this form right here. And again, you know, if you have a big brain and you have memorized your trigonometric functions, you should be able to tell that this right here is a trigonometric function form with a little bit of manipulation, right? So now let's do some u substitution, right? This is a significantly easier problem to solve. Let's go u squared plus 4, right? And our u is just going to be x plus 3, and our du is going to be the derivative of this times dx, of course, which is the derivative of 3 is 0, and the derivative of x is 1. So we just get 1 dx, which is just dx. And that means that we can just replace our dx over here. And this should look familiar. This is a form for the tangent, right? The arctan. And the integral of this is just going to be arctan of u over, and right here, this 4, that's equal to 2 squared. So our a is going to be 2, right? U over 2 divided by a again, which is 2. And if you don't remember this, just scroll back a little bit in the video to when we discussed this before, right? And now we sub our u back in. And so our u, when sub back in, we sub our u back in, we get x plus 3, right? So the integral of this whole thing right here, the integral is just equal to arctan of x plus 3 over 2 divided by 2. That's the whole integral, plus c, of course. But we were able to figure this out because we were able to complete the square and kind of simplify the expression and make it look more palatable, something that we could solve better. Does that make sense? The final kind of technique that you can learn, which you probably already have used it 1,000,001 times when working with most algebraic expressions, is multiplying by 1, right? And all this involves is when you have some type of rational expression, right? Like, let's say 2/3, right? If I multiply this by 1, it's just going to be 2/3, right? Let's go 2/3 again, but let's multiply it by 6. 6 over 6 is still 1, right? This is the same thing, but it gives us 12 over 18. But 12 over 18 is still the same fraction, 2 over 13, right? So we can choose some value of 1, which is some value over another value, to kind of simplify our expressions. And let's see how that would simplify. How would that simplify our expressions in an integral? Let's say you have an integral, right, that looks like this. The integral of 1 over 1 plus cosine x. This is a very hard integral to solve. And the reason is because it involves some bizarre rational expression which you can't exactly split apart. You can't do u substitution cleanly because u substitution of something like cosine x plus 1 requires you to have a negative sign somewhere in there. You need some more techniques to operate on this, and it's called multiplying by 1. So we multiply this expression by 1. But what we choose as our value of 1 may change how we can view the expression. And so for this particular example, I'm going to use 1 minus cosine of x over 1 minus cosine of x. Right? And you know, as you learned in, you should have learned in middle school or high school, when you're kind of simplifying a lot of these rational expressions, or like when you're simplifying radicals, for example, let's say that you have some expression with an imaginary number. What you have been taught, or what you should have been taught, is that you just multiply by, this is best practice, just to multiply by this. Now, I'm not saying that this will be the case with every single example that you ever do, that you're just going to multiply by the constant, you know, minus that value, but it's good practice to do that. So we're going to do that here, right? So we're going to get our 1 minus cosine x over 1 plus cosine x times 1 minus cosine x, right? And if we simplify this further, we get 1 minus cosine x over cosine squared x, right? Because our 1 times 1 minus cosine plus cosine, those middle cosines cancel out so that we just get a 1 minus cosine squared x. And now this might not look easier, but this is a lot easier to solve, right? We can rewrite this knowing our Pythagorean trigonometric identity that sine squared x plus cosine squared x equals 1, right? We can rewrite this as the integral of 1 minus cosine x over sine squared x, right? Because 1 minus cosine squared x, if we just move it to that side, is equal to sine squared x. And now we can use the method of splitting up the fraction, right? And then we can use the method of trigonometric identity substitution, which we'll learn about in a later video, right? And we can split this up as to 1 over sine squared x minus cosine x over sine squared x, right? And then we can further write that as the integral of cosecant squared x, because of that 1 over sine squared x, minus the cosecant x times cotangent, and then find those integrals which are very easily negative cotangent x and cosecant x respectively. But that's all stuff that we're going to be doing in later videos. I'm just trying to get you to understand why this is useful, right? You can multiply by 1 and you can take these very complex expressions that seem impossible to solve. You know, you can reinterpret them, you can simplify them, you can make it so that you bring out some patterns that you may have not seen before. And this kind of gets back to my point, which is when you're solving integrals, you have to be able to problem solve, right? You can't necessarily plug and chug. It requires thinking on your part. And in future videos, in the next couple of videos, I'm going to go through some examples of all these techniques that I've discussed in this video.